just looked at yesterday, we're going to look at some velocity versus time curves. And there's kind of a key concept that we need to get so we can move forward. And this key concept is the area under the velocity versus time curve is equal to the total distance traveled during your trip. So if this is our velocity versus time curve for, say, a car, it means it was going 10 meters per second consistently for a whole 10 seconds of its trip. We can find the distance traveled by finding the area under this curve. Now, if you're a calculus student, you're going to probably have figured out that finding the area under a curve is also known as taking the integral of the function. But for right now, we don't have that, so we're going to use some other methods. We're going to pick some easy curves that we can always find the area of. Right here, guys, if we stay at a consistent velocity of 10, then our velocity was 10 the whole time, and our time was 10 seconds. And so, pretty simple, the area under this curve is going to be the height times the base, or base times height, and we would get our velocity times our time, and we'd come up with velocity times time, which is 10 meters per second times 10 seconds. We cross out the seconds, and we're left with units and meters. And so basically, this car or whatever would have traveled 100 meters in those 10 seconds. Pretty simple, guys, because if we learned this equation before, velocity equals distance or displacement over time. And so if we manipulate that around, we would come up with distance or displacement equals velocity times time, which you can see is what we just did. That's a really, really simple example. It gets a little tougher, not that much, but a little tougher when we start to accelerate. So if we're under a constant acceleration example, that means our velocity is going to be increasing linearly at a constant rate. And in this case, guys, we went from basically zero velocity up to 10 meters per second over a 10-second time frame. Now, we worked with this in class a little bit, but let's hit it again. The area under this curve is pretty simple. It sits right in something like that. And it's easy to see that's a triangle, and we all know from geometry, finding the area of a triangle is simply 1/2 the base times the height, which in this case would be 1/2 the velocity times time. So we have 10 meters per second over here, 10 seconds. We multiply those together, we come up with 50 meters. A distance of 50 meters would be what this thing would travel if it went from 0 to 10 in 10 seconds. Now there's another way to look at it, guys, and this is a way that we're going to look at it quite a bit when we deal with the kinematic equations. And that's coming in with this idea here, that under constant acceleration, if you want to find the average velocity for your trip, you're going to take simply your initial velocity plus your final velocity and divide it by 2, which in this case, guys, if we slide all the way back over here, you can see comes out to be 5. So if I come in here at 5 and I draw a dotted line across here, I'm hoping that all of you guys will see that the area under this dotted line, if I drew that in, would be equal to the area under this red curve. And we can see that, I think, by simply kind of hinging this right here and sliding this triangle back down here, we would have equal area. Now, if we have equal area under both curves, that means we've traveled the same distance in the same amount of time. And if we've traveled the same distance in the same amount of time, we should have the same average velocity, okay? So you can see what I've done over here is I've calculated my average velocity. If we take our average velocity times our time traveled, that should give us our distance traveled. And so in this case, we had an average velocity of 5 meters per second over the 10-second interval, which gives us a distance of 50 meters, which, if we come back up here, was what we calculated was the area under the original red curve here, where we had constant acceleration and our velocity was increasing linearly with time. So I guess just to tie it all together here at the end, the area under the velocity versus time curve gives you your distance traveled. This is a really easy example because it's linear. This one gets a little tougher, but we just have to keep in mind that if we want to find the average velocity when the thing is accelerating and the velocity is very linear with time, we just basically take halfway in between where we start and where we finish. Now, one thing I will throw at you really quickly, because some kids struggle with this, is if we had something like this, and we were at, let's say, 10 here and 20 here, and we didn't start at 0, we would have an average velocity coming in at the 15 mark right there. So in that case, just to verify the formula, we'd say 10 plus 20 gives us 30 times half, or divided by 2 gives us 15. One other thing that I'll throw at you too, since we're here, this is another thing that kids struggle with. If I go from 0 to 10 in, let's say, 5 seconds, and I go from 0 to 10 in 10 seconds, these are velocity versus time curves, then the average velocity for both of those is still at 5, because you spent half your time below the average and half your time above the average in either case, okay? And you'll see in either case, this area right here, if we put that and we rotate it back under there, we still have an average of 5, versus here, which if we take this area and put it in, we rotate it, we still come back to an average of 5. So if you are accelerating linear, or you're accelerating constantly, or your velocity is varying linearly with time, it doesn't really matter how long it takes you to get to that time. If you're constant, your average is still going to be halfway in between. And that's, I guess, velocity versus time curves.